Why might scientists be interested in comparing these two synthesis methods? And how could the presence or absence of chemical inhibitors affect the structural or vibrational properties of the resulting materials? When Raman spectroscopy is used to analyze these samples, what kind of information does it reveal? And how are vibrational features linked to the atomic composition and bonding in the material? Can Davis Surins manufacture solid-state sodium-ion batteries made from seawater in Latvia? How do the Raman spectra of these materials differ under different synthesis conditions? And what do these differences suggest about the structural arrangement of ions like Fe, Mn, and Na within the framework? In the Raman spectrum shown in figure 2.5, what is the significance of the observed intensity peaks at 2132 cm superscript 1 and 2092 cm superscript 1? And what do these peaks tell us about the presence and behavior of Fe ions in the material? Can these peaks be interpreted as signatures of specific coordination environments involving iron and manganese ions, particularly those involving Fe2 cyanide bridges to Mn3 as represented by FiCN Mn3? Why is this type of vibrational mode important to identify, and what does it reveal about the oxidation states and bonding interactions between metal centers in the PbMen framework? How can the presence of one divalent ion like Mn superscript 2 and nearly 2 sodium ions in the composition be inferred from the spectral features observed, and why is this ratio significant in confirming the material's composition? What does the increase in peak intensity tell us about the concentration or coordination strength of these metal ions? Could it indicate that more of the FiCN Mn3 bonding units are present, or that they are more strongly ordered in the material? How does the presence of Na ions contribute to the overall charge balance and structural stability of these PbMen compounds, and can their indirect detection through Raman peak shifts be considered a reliable method for assessing composition? Why might changes in synthesis conditions, such as the inclusion of chemical inhibitors, affect the Raman signals? Could inhibitors alter the rate of crystal growth, the local environment of the metal ions, or the degree of crystallinity? What can researchers infer about the material's internal structure or electronic properties based on these spectral changes, and how might such insights help in optimizing the materials for specific functions, such as catalysis, energy storage, or sensing? In broader terms, how does Raman spectroscopy enable scientists to probe and compare the fine structural differences between materials prepared under different conditions? And why is this important for advancing material design and functional performance?